Say a car is traveling at a constant velocity of 10 meters per second. The car's initial position at time zero is 100 meters. We want to plot the acceleration versus time and the velocity versus time. So we want to be able to extract from the wording certain things that are going to help us draw the graphs. So one key wording to look for here is constant velocity. The velocity is not going to change. It's going to remain 10 meters per second throughout time for the whole 10-second interval. So when we go to plot the velocity, we want to start it at 10 meters per second and have it end at 10 meters per second. And it's just going to be 10 meters per second all the time. So it's going to make a horizontal line as a graph. Alright, so one of the other things that we know from constant velocity is that is another way of saying that the acceleration is zero. So there won't be any acceleration. That means this will just be a horizontal line on the time axis. And there we go. We sketched the velocity and the acceleration so far. Now eventually what we want to do is we also want to sketch the position versus time. Notice that they say at time zero, the initial position is 100 meters. So that's actually one fact that we can use to get started on graphing it. And then that's going to be the location on the vertical axis where we start our graph. Alright, so before I graph the rest of this, let's see what B says. For this question, let t equals 0 be the initial time. Then choose a final time, TF equals 10 seconds. We actually want to shade the area underneath the velocity curve because that area has meaning in physics. Alright, so here's our t equals 0. That's the start of the interval. Here's our t equals 10. So we have ti and tf. Now we just want to shade the area under that function. Alright, so Sir Isaac Newton, famous physicist and mathematician, developed the mathematics of calculus to explain physics. And one of his great insights in physics was that he realized that the area under a curve has meaning. For example, we have the formula delta x equals vx times t. Now, if you look at this rectangle that was created, check out the width of it and the height of it. And what are those dimensions? Well, the width of it is a time interval. Could be called a delta t. And the height of it is a velocity. If you multiply a velocity times a time, then you get a displacement. The area under that curve has meaning in physics. The meaning is that the area is equal to the displacement of the object for the time of 0 to 10 seconds. So in order to be really specific when we write it, we want to say delta x, displacement, and then we further want to say what the time interval is. So we're going to go from t equals 0 to 10. And the units are seconds. And how do we find this? By multiplying the height of the rectangle, which is 10 meters per second, times the elapsed time, which is going to be 10 seconds. According to this calculation, the displacement for that time interval will be 100 meters. This will help us construct the rest of the graph, because what we can do now is we've got an initial position, which we could call xi. We want to have a change in position, and we want it to be positive 100 meters. So after 10 seconds, we go up 100 more meters, and then that's going to be our final position. The change in position is going to be the green arrow here. So there we go. We found 2 points that will be on our position versus time graph. So there won't be any displacement if no time has passed. So we're actually going to start off with a displacement of 0. Haven't gone anywhere yet. And then what our calculation above shows is that after 10 seconds, we're going to go up 100 meters. Now also, our initial position at time 0 was given in the problem. That was 100 meters. It's the height of the red arrow here. But then what's our final position? 200 meters. All right, so now what we'd like to do is we'd like to come up with a general equation that will give us the displacement of the car no matter what the final time is. So the general formula is actually simply this formula. Delta x from t equals 0 to some final time equals the velocity times that time. Or in other words, if we want to simplify it, delta x equals vt. Notice the velocity here is constant, so I don't have to actually put the bar above there. The bar means average, but the average velocity here is just going to be 10 because it's 10 all the time anyways. So now let's put in our numbers. And that is our formula that we want to use for the displacement. We can just plug in a time and it'll give us the displacement of the car. It's pretty cool. So plug in t of 2 and our displacement becomes 20 meters. Now we can add that 20 to the original 100, showing that our new position for the car will be 120 meters. And we can go to our graph and plot that as a point. All right, plug in a time of 4 into the equation. You get 10 times 4, which is 40 meters. Add 40 to the original 100, and we're now located at an x of 140 meters, which will be here. And I think you can see the pattern of what's going to happen here. This is constant velocity, so the velocity is not going to change, and our position versus time graph will be nice and straight. Okay, there we go. Let's go ahead and connect the points. All right, that's a great graph of constant velocity. Our last job here is to come up with an equation for the position of the car. So for that, we can use x as a function of time equals the velocity times the time plus some initial position. A little bit different formula than above. Now, how do we get that formula? Well, let's remember that delta x can be rewritten as x final. Can be rewritten as x final minus x initial. Now, if we simply add xi to the other side, then we'll get x final equals vxt plus xi. Okay. Now, we just want to plug in our numbers. So we have 10 meters per second for the velocity, so we'll have 10 times t. And then our initial position for the car was actually the 100. So this will be our formula that gives us the positions of the car. Now let's just check it to make sure it works. Plug in a time of 0, for example. What would you get? You'd get 100, which does agree with this, right? Now plug in 10. 10 times 10 makes 100, plus 100 makes 200. So it looks like we've done it right.